Okay, I think we're ready. So thank you for joining us for today's webinar, best practice of using the Prewet Deicer for winter mobility in the Pacific Northwest. Today's webinar is being hosted by CAMMSE, which is a Center for Advanced Multimodal Mobility Solution and Education. We are a Tier 1 university transportation center funded by U.S. Department of Transportation under the FAST Act. We are a consortium of 5 universities led by us at the UNC Charlotte. We also have University of Texas at Austin, Texas Southern University, University of Connecticut, and Washington State University. So before I introduce our speaker, I would like to cover a few housekeeping topics. So today's webinar is being recorded, so we will be able to share a link with you after the event is complete. And then we welcome you to revisit the content yourself and share with your colleagues. We also invite you comments and questions that you may have. Please look at a Q&A chat box on your screen. If you think of a question for the speaker at any point, just type it there, and we will hold it for the discussion portion at the end of the presentation. So today's presenter is Dr. Xianming Shi, who is a professor of the Department of Civil and Environmental Engineering Department at the Washington State University. He's also associate director at the Washington State University, obviously, for CAMMSE. So at this time, I'm going to hand it over to Professor Shi, and who is going to start today's presentation. So Dr. Shi, is all yours.
Excellent. Can you hear me all right?
Yes, I can hear.
Okay. Thank you, Professor Fan, and thank you for everyone for joining us, for taking the time to go over this, hopefully within the hour. And today I'd like to share with you some recent research we completed. Again, the title is Best Practices of Using Prewet Deicer for Winter Mobility in the Pacific Northwest. My name is Xianming Shi, a professor in civil engineering at Washington State University, and also a site director here for CAMMSE. Now, today I'd like to share with you several topics, I guess. First, we'll start from why best practices are needed in winter road maintenance operations, and then we'll move on to discuss the multiple dimensions of winter road maintenance operations, and then zoom into one best practice, which is pre-wetting, especially in the Pacific Northwest. And then based on an in-depth survey, we designed some lab work to investigate how the current practices of pre-wetting contribute to winter mobility, whether or not they actually are best practices. And then we'll conclude with some remarks. The photo on the left, on the bottom left, shows a pre-wetting equipment, basically putting liquid deicer onto solid salt. This is a practice called pre-wetting. We'll talk more about it. But with the pre-wetted salt, then it's applied onto the roadway, as you can see in the middle photo. So this helps to reduce bounce and scatter and make the deicer work faster and so on. So there are a number of benefits we'll talk about in more detail. And one reason we're doing this is to try to minimize the amount of salt we need on the pavement to maintain a certain level of service during winter weather, without, of course, compromising the environment, without compromising the safety of mobility. So let's start from why best practices are needed in winter road maintenance operations. This is a bigger picture. Actually, this picture is from Washington State DOT, I think is Snoqualmie Pass in the wintertime. So if we start from winter mobility in the nation, there are direct and indirect costs. This is a graphic I've used many times. According to the Federal Highway Administration, more than 70% of roads and roughly 70% of population are in the snowy region, in these blue circles, as you can see on the right. Usually these refer to, excuse me, these refer to areas having more than 5 inches of snow each year. And according to the Federal Highway Administration, the highway departments in the US are spending approximately $2.3 billion each year for snow and ice control on highways. And then the indirect cost to the transportation infrastructure is another $5 billion. Of course, when we do such winter road maintenance operations, we tend to put on deicers, anti-icers, and abrasives on the pavement to maintain the friction of the winter pavement. And these materials can migrate into the adjacent environment through multiple pathways. And one of which, as you can see in this graph, I put in the red circle, is they can be basically suspended as dust or be transported by wind and currents into the adjacent soil, vegetation, and so on, and then pose short-term and long-term risks. Talking about long-term risks, chlorides, which are typically used as freezing point depressants in deicers and anti-icers, and they tend to be highly corrosive and highly mobile, water-soluble, and nearly impossible to remove without cost-prohibitive approaches. So they do quietly accumulate in the environment, and over the last 5 or 6 decades, we have increasingly seen, evidence that this is becoming a long-term risk to water bodies. Now, part of the reason we still need these abrasives and deicers and anti-icers because winter weather tends to negatively affect traffic mobility. In the wintertime, the general public wants to still drive relatively fast from point A to point B. But as you can see with winter weather, different case studies, of course, are reporting different numbers. But in general, we're seeing significant reductions in free flow speed, in traffic volume, as well as in traffic capacity. Depending on the snowfall intensity and the amount of traffic volume and the specific road weather scenarios, of course, the level reduction would differ. This basically calls for the need for winter road maintenance operations. And one study we did back in 2013 basically looked into the cumulative studies out there and kind of linked the road surface condition on the left to the speed reduction factor on the right. As you can see, if we are doing winter road maintenance, such as with chemicals, to make the surface chemically wet, the reduction, is minimum, 4% speed reduction. But if we are talking about the very bottom one with snow covered and no winter maintenance actions, then we're talking about 16% reduction. Another study done by Professor Wolf Nixon's group back in 2009 looked into tens of thousands of cases from Iowa highways and developed this empirical equation to basically define this or predict the traffic speed as a function of wind speed, road surface condition, with or without plowing action, and then the chemical application rate. Of course, we'll also talk about chemical application rate in this talk later. So in general, we're looking at mobility benefits from winter road maintenance operations. On the one hand, we're seeing, of course, less reduction in the average speed. But on the other hand, of course, as we mentioned earlier, there may be some implications on traffic volume as well. So winter road maintenance operations are vital to economy and safety. In addition to improved mobility, we're also looking at fewer accidents, reduced travel costs and reduced fuel use, reduced vehicle emissions, energy consumptions, sustained economic productivity, continued emergency services, One case study we did for Minnesota Department of Transportation looked at their current practices over the last few years, and we quantified how much benefit we reap from such operations, looking at basically avoided traffic accidents, improved mobility, and improved fuel efficiency, and so on. So we examined the historic data and came up with approximately $220 million per year as benefits. And this doesn't count the lower risk of highway closures. That's some additional benefits. So we're talking about a benefit to cost ratio greater than 6.2, which means for each dollar you invested in Minnesota DOT's highway winter maintenance operations, you reap at least $6.2. So that's highly desirable, but on the other side of the equation, we're looking at the environmental risk because their current practice puts approximately 9 tons of salt on each lane mile each year. So when I look at the EPA's drinking water limits for chloride ion, approximately 250 milligram per liter, that translates to sodium chloride or salt at 379 milligram per liter. So then we can calculate that each year at the rate it's going, we could contaminate up to 5 million gallons of groundwater. If we multiply that by 4 lanes, typical highway, 4-lane highway, and then over 50 years, like I mentioned earlier, these chlorides are nearly impossible to remove from the environment once they're in the environment. Then we're talking about up to 1,000 milligallons of groundwater at risk. So that's a tremendous number if we look at long term. Now, if we look at the national situation, the same conclusion can be made that salt reduction is essential because you look over the years, especially starting from 1960 to, this chart is a little bit old, so we're still not looking at 2020 yet, but at least look at those 40 years, and you're seeing exponential growth in salt usage for winter road maintenance operations on highways, especially. And this basically leads to this dotted lines where we're talking about the chloride concentration tested in rural rivers feeding Baltimore water supply reservoirs. This is a case study. And look at over the 40-year time period, the chloride concentration increased 3 times. So of course, if you look on the right-hand side, it's still not reaching 250 yet, but at the rate it's going, basically there's no going back. In other words, if we are thinking about social dilemma, the general public wants to drive fast during winter weather, so requires the agencies to put down deicers, abrasives, and so on. But then these are basically dealing with long-term risks, whether or not our grandkids will be drinking salty water. So agencies face emerging challenges. They have a lot of different priorities. At the center of this chart is level service or customer satisfaction. But then there are other priorities such as safety, mobility, productivity, and everything has to be done in a cost-effective manner with minimum corrosion to vehicles and to infrastructure and being good steward of the environment. Again, sometimes these priorities don't align with each other very well. Sometimes they compete with each other. And the bigger context is also there are increased traffic volumes, higher customer demands, and funding, staffing, and technology constraints. So with all these in mind, one can argue that we need best practices. We need the best possible science, technology, and practice to find a way out. So if we look at the left side of the slide on the top, these are some of the, on the left basically are the typical winter road maintenance practices. The very top one is anti-icing. The sequence of events typically is if we have really good weather forecast, knowing the snow is coming, we would, the agency would send out trucks to put down typically liquids for anti-icing, which aim to prevent the bond of snow ice to the pavement. And then if that fails, or the forecast was off, or for whatever reason the bond formed, then you need de-icing, which is the photo, second photo on the left, from top down. And usually these are solids, even though in light snow events, you could use liquids for de-icing as well. Now, if with de-icer, usually what you intend to do is not to melt the entire amount of snow ice on the pavement. That's nearly impossible. That would take too much salt. What you do is basically break the bond between the snow ice and pavement so that the bond is weakened or broken, and then the snow and ice could be removed by mechanical means such as plowing here at the third photo. But again, sometimes even plowing, de-icing, anti-icing, all of them still couldn't give you a level of service you want or the level of friction coefficient you need. Then you're resorting to sanding, putting abrasives on, which provides a temporary traction layer. So these are the typical practices for winter maintenance. Today, of course, we'll focus on mostly the de-icing practice with the liquids being used to pre-wet the salt so that the salt can stay on the roadway better and longer. Now, on the right-hand side, we'll talk about the implications. Certainly there are environmental risks such as, stresses posed to vegetation, soil, aquatic species, and then there's also negative implications on concrete bridge decks, concrete pavement, asphalt pavement, motor vehicles, steel bridges, and so on. So we're basically doing this balancing act, trying to achieve the best possible mobility and safety without jeopardizing the other priorities. So in that bigger picture, pre-wetting, like I said, is just one of the best practices, putting liquids to solids. A case study, for instance, has demonstrated that pre-wetting abrasives can reduce the need for application by 50%, which is very helpful. Now, what about pre-wetting the solid salt with liquids, whether it's salt brine or some other chemicals? So over the years, the agencies have learned that there are multiple benefits in that practice. For instance, reduced or minimized bounce and scatter. So you're not losing the applied dry salt to the traffic. And also by pre-wetting the salt, you increase the longevity of the salt on the road, and that translates to less frequent applications. The liquid also helps to speed up ice melting and penetration process and improve the de-icer performance, because the solid de-icer needs to turn into a liquid form before it starts to melt the ice and penetrate the ice and undercut the bond of the ice to the pavement. So even though agencies have learned over the last 10, 15 years, pre-wetting is a good practice, but it hasn't been systematically studied, especially when it comes to optimum pre-wet rate or product type. But as we know, if we can come up with best practice in pre-wet, we can put less salt into the environment. So there are a lot of implications in terms of mobility and safety, environmental stewardship, infrastructure preservation, equipment preservation, and economics. So if we look at the multi-dimensional implications of winter road maintenance operations, just to refresh your memory, on this chart, we'll mostly focus on the right-hand side. If you look at the top, we see an unhappy face with vehicle corrosion, infrastructure deterioration, soil pollution, vegetation deterioration, decreased water quality and air quality. But on the bottom of the chart, we're looking at a happy face with a safety enhancement or enhancement in efficiency and mobility. So again, it's a balancing act, and the best way out is to adopt the science, technology, and best practice. Now, if we look a little more into some of these dimensions, one piece of the puzzle is the vehicle risk of de-icers. The current numbers estimate roughly $2.8 billion as a deicer corrosion cost to motor vehicles. And again, these deicers are mostly chloride salts, sodium chloride, magnesium chloride, and calcium chloride. And we have a lot of vulnerable metals on the vehicles, such as carbon steel, cast iron, and other alloys. And about a quarter of these costs are preventable. But that requires, some sort of coating or the best possible material selection and so on. And then if we look at infrastructure risks of deicers, the first one on the list is hydraulic cement concrete. They can be compromised by the exposure to deicers, as I'll mention a little bit in more detail in the next few slides. And then there's also risk to asphalt pavement, to embedded steel rebar dowel bar, and also to steel bridges, pavement markings, and barriers, and so on. Again, there are a number of papers published, so if you're interested, you can look into those details. Now, there are two interesting recent studies I want to share with you. One of them is this supposedly environmentally friendly deicer, potassium acetate, which is at least 10 times more expensive than sodium chloride, actually 20 times more expensive. And it's typically used on airfield applications and also for highway departments, usually for fixed anti-icing, fixed automated spray technology on bridge decks. But we took some bridge deck cores and we found actually this deicer also posed a significant risk to the concrete, especially compromising its compressive strength and spring tensile strength and micro hardness. Now, depending on the type of deicer we're talking about, the concrete would fail differently. For instance, we simulate this kind of exposure in the lab in an accelerated manner. And at the top, you can see on the left, we're talking about a phenomenon occurring at a very fine scale. If our hair is about 80 microns in diameter, then this is about 10 micron by 10 micron area. You're seeing some beautiful crystalline faces forming inside the concrete. And the sodium chloride, you're seeing another type of crystalline face. So what's happening is basically the concrete was losing calcium and then forming new crystals. The calcium leaching behavior basically makes the concrete weaker and it's compromising the gel which holds the concrete together. It's very similar to when humans age. When we age, we lose calcium and our bone gets brittle. So this is a very similar phenomenon and very concerning. Now, another common type of freezing point depressant is magnesium chloride. Unfortunately, this also reacts with the cement paste. We found the same thing, on the right-hand side, you're seeing, the hollow, porosity basically left behind by the calcium leaching behavior. And then you're also seeing the crystalline phase formed in this process. So we detect significant loss of tensile strength and micro hardness from the field bridge deck cores. What's even more alarming is that these type of degradation often peak inside the concrete. So on the surface, you are not seeing any sort of surface distress. Typically, there's no cracking or permanent deformation. So in other words, if a bridge engineer goes out there every 2 years, inspect the bridge deck, they rate the bridge deck 9 out of 10. But when you take a core, sometimes you're losing half of the strength. That's very concerning. Now, shifting gears to environmental risks, I already talked about chloride salts being highly soluble, mobile, and difficult to remove or being conservative. There's another piece of this is they also mobilize the heavy metal out of the soil and the vegetation. So that's an environmental risk. Now, what about the non-chlorides? I already mentioned the potassium acetate, but there's also potassium formate, glycols, and other agricultural-based products. Their problem is not so much in the long-term risk because they tend to degrade in the environment, but short-term risk to water bodies is relatively high because they have a high oxygen demand, talking about biological or chemical oxygen demand. Usually, this means when they enter when the storm water carrying the deicer into the environment, they tend to be stimulating the growth of microbes and consume the oxygen in the water, and therefore make the fish or other frogs and so on at risk. In addition to the freezing point depressants, we also have some additives in these products, such as corrosion inhibitors, surfactants, and so on. They also pose toxicological risks to the species. So in recent years, we're seeing efforts, including my own lab, in developing greener deicers. Here's one case study where instead of using the beet juice, which is a common green deicer active, we want to further reduce the oxygen demand of this material. So we end up using the waste sugar beet leaves and use a patent technology to derive green chemicals out of the waste leaves. And then we blend it with brine, of course, in this case, reduce the chloride loading and then improve the ice melting friction and reduce the oxygen demand compared with the typical green deicer out there, which is a blend of salt brine and sugar beet juice. And then we look at, okay, as an agency, how do we make a decision? So given a set of user priorities, we can develop some decision ways for each dimension of the problem. And then we can come up with a process to come up a composite index or score. So the best performing one, as you can see here, mixed one, we had a score of 92. Which is out of 100, not too bad. When we look at the control, which is straight salt brine, we have an index or score of 14. So that's one way we illustrate how you could make a decision taking all these dimensions into consideration as well as your priorities. So now shifting gears to pre-wetting practices, especially in the Pacific Northwest, which is one piece of the puzzle. And we start from a national overview. So a recent survey, we collected, response, as you can see in this map, from 30 some respondents, and then overall we're seeing that again the overall picture is still pretty much the same as we surveyed. I want to say at least 10 years ago. Mostly people are still using rock salt and abrasives as solids, and then using sodium chloride, merchloride, and calcium chloride as liquids. And there's a little bit newer trend, which is the use of beet juice is becoming more popular as an enhancer. The typical blend for anti-icing is you blend beet juice with the 23% salt brine, 23% sodium chloride brine at 10 to 90 volume ratio. And for de-icing and pre-wetting, the beet juice dosage is higher, typically 30%. So the beet juice is drinkable, but doesn't necessarily mean it's that friendly to aquatic species. Again, the issue was oxygen demand when they enter the water bodies. About 2/3 of the respondents use corrosion inhibitors. Like we mentioned earlier, that also would pose a concern for toxicity. Now, nationally, we're talking about typical application rate of 7 to 15 gallons per ton of solid salt. And according to literature, that number is a little bit, that range is a little bit narrower, 8 to 12. Usually it's a function of how large your salt particle size is. And then there's also a very interesting deviation from the typical pre-wetting, which is a slurry. Basically, you intend to greatly increase the pre-wet rate so that it works faster, but that requires your truck has the pumps to make the salt slurry. So sometimes the equipment is limited and you cannot go up as high as 30 to 50 gallons per ton. Now, when we zoom into Pacific Northwest here, we're talking about Alaska, Idaho, Washington, Oregon, and we're seeing a similar situation. Most commonly used pre-wet rate is 10 to 12 gallons per lane mile, but we also see 1/3 of them use more than 15 gallons per lane mile. So which one's better, right? That's the question we'll investigate in the lab program. Now, we're also seeing that most people actually use salt sand as well as salt sand blend, depending on the situation, and the blending ratio also differ greatly. And again, we're seeing the same kind of liquids being used. The application rate of the pre-wet salt is truly a function of pavement temperature and snowfall intensity. So typically, according to the survey responses, we're looking at 50 to 400 pounds per lema as for salt. And for sand, it's up to 800 pounds per lema. As I mentioned, the sand is not intended to do much. Actually, it's only providing a temporary traction layer. So whenever we can, we actually don't want to use sand because it's very difficult to recover that from the environment. Now, looking at the lab investigation, now armed with all this knowledge, what people typically do in the field, we want to design some work in the lab so that we're doing things in a more controlled environment and hopefully produce reproducible results. So the first question in mind is, does pre-wetting contribute to ice melting? So we end up using a type of using a salt which is a little bit finer than the salt being used by the Washington State Department of Transportation, partially because if they're too large, the reproducibility will suffer. So in the field, also because of the high volume and high speed traffic, the larger particles tend to be crushed anyway. So we're looking at these salt particles finer than number 4 sieve or 4.75 millimeter. So then we basically look at two scenarios, 25 degrees Fahrenheit or 15 degrees Fahrenheit on pavement. Those are not too extreme winter weathers, which are so these are typical pavement temperatures we're seeing in the field. And then we're looking at 5 different liquids, the typical 3, sodium chloride, the salt brine, and then calcium chloride, microchloride. And then we're looking at the beet juice blend at 20/80 volume ratio. And then we're looking at the WSU grape pomace extract, which is a newer patent additive at, of course, much lower dosage, 3% by volume in the blend. So we'll look at these 5 liquids and see which ones perform better in terms of, mobility benefits. The first one is, yes, the pre-wet salt actually generally improved their ice melting capacity at 25 degrees. Here, of course, we have to look at which pavement temperature, 25 degrees. And also, we end up using a higher than usual application rate of pre-wet salt because otherwise, there's simply not much salt to be applied on that ice layer, and then the error range will be too high. So in the lab, we had to go with a higher number. So that's the limitation of the lab test, but still tells us, at relatively warm temperature of the pavement, the pre-wetting actually helps the ice melting. Now, what about a colder temperature, 15 degrees? In this case, we further bumped up the application rate of pre-wet salt, and you're still seeing the benefits. Well, actually, I forgot to mention, on the left-hand side, we're talking about 8 gallon per ton pre-wet rate. On the right-hand side is 16 gallon per ton. And the trends are very similar, but in the colder temperature, the differences between the pre-wet liquids, however, sort of diminished. If we go back, here, this one, we're seeing much more different behavior. When it gets colder, the type of products actually don't make as much difference. But they're all better than the blue line, which is the control with the dry salt. Now, the interesting thing is that the pre-wetted salt actually doesn't always improve the ice melting capacity. For instance, we did some statistical analysis, this two-tailed student t-test. As you can see in this scenario, we're looking at a warmer temperature, 25 degrees Fahrenheit or minus 3.9 degrees Celsius, and 2,000 pounds per lemma, which is a high application rate. And you are seeing some negative numbers indicating lesser ice melting capacity for pre-wet salt. So, of course, that's giving us some interesting questions, but this needs to be further validated in the field, of course. Now, another thing is, what about the speed of ice melting? We look at 15 minutes. Sorry, I forgot to mention earlier numbers were all 60 minutes. So what about 15 minutes? Do the pre-wetting, like most practitioners would imagine, should speed up at the rate of ice melting? Yes, they do in most cases. Again, statistical numbers, if the number is smaller than 0.05, we think there's significant difference, statistically speaking. And yes, in many cases, it's statistically different. Now, what about the other piece? Ice melting is one piece of the puzzle, but also we talk about in the field, we try to simulate the sequence of events in the lab. This is done at Montana State University. Basically we start from making our own snow, compact the snow, age snow, and put down the pre-wet salt. As you can see, the amount is really small. Again, they're not the salt is not intended to melt entire amount of snow and ice. They're just intended to have the ice melting penetration and then undercut the bond. And then you have this simulated traffic. We do 500 passes, but under relatively low speed because it's hard to simulate 40 miles per hour in the lab. And then we start testing the bond strength and friction coefficient on the pavement afterwards. So one thing is that the pre-wetting generally decreased the pavement friction, which is a surprise to us, of course. The only good news is that for the beet juice blend, at a low application rate, 8 gallons per ton, we're seeing dramatically improved friction. Much more so than the control. But in most other cases, we are looking at lower numbers, which is undesirable. So what's going on here? We actually want the higher friction coefficient. Usually, just to give you an idea, any number lower than 0.3 or 0.4 would be slippery pavement. So one possibility is the excessive moisture we introduce. Keep in mind when we are putting especially a high pre-wet rate, we're introducing a lot of water into this mix. The other possibility is the application rate. The field study in Ontario basically is looking at, is suggesting 44 gallons per ton as a better better pre-wet rate. The caveat of the lab test is that, again, we didn't have sufficient amount of traffic, even though 500 passes wouldn't probably be sufficient. And more importantly, the speed of the traffic is not as high. In the field, you are dealing with higher speed, so it will agitate the pre-wet salt into the ice layer much quicker and much more thoroughly. So that's the inherent limitation of the lab test. But the good news here is pre-wet generally reduce the bond. With two exceptions here. One is when the salt brine was at 8 gallons per ton, and another one is beet juice blend at I think it's 24 gallons per ton. But in most other cases, we are seeing the benefit of reduced bond, especially when the beet juice, again at 8 gallons per ton, seems to be reducing the bond by roughly half. So to summarize, pre-wetting is commonly performed by Pacific Northwest state DOTs, most commonly at 10 to 12 gallons per ton rate. And pre-wet material application rate vary from 50 to 400 pounds per lane mile for salt, and up to 800 pounds per lane mile for sand, depending on pavement temperature and snowfall intensity. And pre-wet salt produce similar or less ice melt at higher application rate at warm temperature, but the pre-wetting is beneficial to initial and terminal ice melting for lower application rates at warm temperature like 25 degrees, 1,000 pounds per lane mile, and cold temperature. Considering both temperatures and application rates, the best to worst list is here. The calcium chloride brine is the best pre-wetting liquid according to I have to add a disclaimer, is under the investigated conditions in the lab. And then the grape pomace extract, the second, and then the beet juice blend, and then salt brine, and the worst was magnesium chloride. One thing to clarify is that in the lab, the relative humidity is about 20%. So we're not, the worst performance of mag chloride is not due to the hygroscopic nature. It's not grabbing much moisture from the air. And also calcium chloride could do, calcium chloride is similar to macrolide in terms of being hygroscopic, but that seems to be not the reason. Also, in the lab test, pre-wetting did not show a consistently beneficial impact of increased friction or reduced bond strength. That's interesting. And again, a disclaimer is that we only have 500 passes and this very low speed, and the pressure was only 16 psi instead of a typical, maybe 50 or 70 psi by trucks. And additional tests might be needed for statistical confidence in the results. And the best performing pre-wet liquid, if we're looking at friction and pavement snow bond, was beet juice modified brine at 8 gallons per ton. Well, here are a few concluding remarks. Again, there are limitations in the lab test. Even though I mentioned earlier, the beauty of the lab test is you control the conditions, but we are not simulating the bounce and scatter from really high speed unless we have a better instrument to simulate that. And also, the speed was the traffic was slow and light. And for the field test, hopefully, if we look to the future, if we can convince agencies to conduct field tests, then we can gain more knowledge. And these are the aspects we want to really examine, or the type of hypothesis we want to test. Whether or not, pre-wetting reduce bounce and scatter, reduce overall application rates without jeopardizing friction, of course, improve friction, reduce time to regain bare pavement, increase longevity of materials under various speeds. Now, just to give an image of what's happening in the field, there are a lot more factors at work. For instance, the humidity could fluctuate, and you could have different rate and type of precipitation, and the water content of snow will be variable depending on where you are. Minnesota versus Montana would be different. And air temperature could play a role. Solar radiation, especially the color of the product or the thermal properties of product may play a role. And then there's also wind speed and direction. And also, if you look at pavement, pavement temperature is one thing we control in the lab, but there could be pavement type, asphalt versus concrete will behave differently. The texture and the condition of the pavement also would, play some role in this. So it's pretty complicated in the field. That's why we start from a lab test to gain some basic baseline knowledge and see under the well-controlled conditions how things behave. Now, to acknowledge the fundings from Tier 1 UTC CAMMSE, the match was from Washington State University, and we thank the several respondents from state DOTs and industry. We also had team members Yan Zhang and Michelle Aiken, and Nathan Card and Eric Forrester were helping us in some of the tests. Now, with that, I welcome your questions. I see people have typed some questions in the chat box. I haven't got a chance to look at them. Maybe I should stop my share so I can, or maybe there are questions. So Professor Fan, if you could actually read out the questions for me, it would be better. Otherwise, I have to stop sharing before I can see them.
Yeah, thank you, Dr. Shi, for your great presentation. Yeah, we do have one question here. The question is about those photo micrographs. So the question is this, okay? You keep referring to them as being from cement paste. Are these images from field samples of a concrete that is being treated over years with acetate salts, or are they made in the lab and treated there?
Okay, very good question. Yeah, for the sake of time, I probably didn't go into that detail. Let me go back. Yeah, like this one, for instance. Yes, anything on the right actually are lab samples, but we're seeing the same phenomenon in the from the field samples too. That's one thing. The other thing is these samples actually were concrete samples made in the lab. when I refer to cement paste, because we found the reaction mostly, well, actually only occur in the cement paste phase of the concrete sample. So the way it went was like this. We conducted a 3-year systematic study, look at, well, mostly it was part of a study sponsored by Oregon DOT. We look at thousands of bridge decks in the database and then randomly selected some representative ones. I think we called with the help of DOT, we obtained cores from at least a dozen bridge decks, and we're the only exposed to, I should go to this one, only exposed to mercury over the last 15 years. And because we didn't see any surface distress, and the rating by the DOT usually was 8 or 9 or sometimes 7, but when we look at the strength numbers, we were really concerned. Then we try to figure out what's going on and look at the macroscopic evidence. And then in order to reproduce that, we further conduct some lab tests, which are accelerated, of course, to reproduce this phenomenon. I hope that clarifies.
Yeah, thank you. So do we have any other questions? Looks like we have one only here. Let me go down, huh? Yeah, the second, we do have another one, said additives aside, is there a practical way to predict how much organic deicer would be needed to be introduced to a water body before low DO becomes a problem for ecology?
Very interesting question. Yeah, for the, this is referring to oxygen demand issue. As we know, there are other things contributing to the oxygen demand, right? Like fertilizers or deicer products from the parking lots and other places, commercial facilities. So what the highway is contributing to the water bodies is one piece of the puzzle. I think USGS has done some great work over the years, field monitoring, and probably are better equipped to answer that question. But what I see is just when we look at beach juice, for instance, we because it sounds so green, we can drink it. We assume it's not a problem. It's green. It's sustainable. But I just want to raise the awareness. Actually, they're not as green as you might imagine, and there are some issues with them. So really, we're looking at a multi-dimensional issue and trying to achieve a best possible or a balanced solution within all the constraints. Additives are certainly one way out, because in the short term, at least, I don't see people get rid of the chloride salts altogether because they're relatively affordable. I mentioned the acetates were 20 times more expensive, roughly speaking. So yeah, we still have to use chlorides. So most agencies are doing salt reduction program, trying to minimize the amount of salt without compromising safety and mobility. So there's some room for improvement in those regards. I mean, both in management domain and in technology domain.
Okay, thank you. And the next question we have here is, in the cost and benefit part, did the cost of an accident consider the injury severity? Since some previous research has pointed out that lower travel speed in snow weather could mitigate the crash injury damage severity.
Very good question. I want to say we didn't get to that level of detail, but we did differentiate. This is like a decade ago, so I don't remember the specific details. But we did differentiate the property damage only accidents from the fatal accidents. That's for sure. But we probably didn't consider the level of severity, change due to the winter maintenance actions. That's really interesting point. But we didn't get that far into it. What we did was look at tremendous amount of data from their historical practice over the last 3-4 years. The details were actually published in that TRR paper. There's also a final report which with a lot more details. Yes.
Okay, thank you. So we have 2 more questions, and the second to last one is, water contents of snow is an interesting variable. especially when considering pre-weight. Was there any way to modify water contents of the snow when evaluating pre-weight effectiveness?
Very good question. Yes, of course we could measure. Yeah, yeah. In this case, I think we probably did not report the moisture content of the snow. The ones we made, I think, is relatively dry snow. Well, prior to, well, it's kind of hard to get to that page, but prior to this practice, sorry, just a sec here. Yeah, the moisture content, like I mentioned, Montana certainly will be greatly different than Minnesota. So it's not easy to, well, it's actually pretty dangerous to transfer the knowledge, directly apply it from one state to another if your smell is significantly different. So in this case, the moisture content is relatively low. It's a drier snow, similar to what typically we see in Montana, but at least they're better than the old practice where we're basically using ice particles to simulate snow. But back to that question, yes, we certainly could measure the moisture content of snow, for instance, by collecting the snow and figure out the volume versus weight. Yeah, we can figure out the moisture content.
Okay, thanks. And the next one is, will this study allow MDSS to provide a credit for lower volumes of a chemical to melt ice or just break the bond?
Interesting question. Yeah, I think we cannot rush to that recommendation yet because, again, this is a kind of like exploratory study trying to put things under controlled conditions and see what are the challenges. For instance, we basically reveal there are certain things might be contradictory to perception. So, but in order to get to the level of recommendations, to be adopted by MDSS, I think there needs to be one additional step, which is a field test or validation. Oh, by the way, for those who are not familiar with MDSS, which is a maintenance decision support system, usually a one-stop shop for all the current and future road weather conditions and decision-making tools.
Okay, thank you. So do we have any further questions here? The one I asked just pretty much the last one.
Well, again, the slides will be online, the recording will be online, and feel free to contact me for, follow-up. Yes, I think my contact is in the very last slide too.
Yeah, that'd be great. So if we do not have any further questions, so our webinar will end here. So thank you all very much for taking your time attending our webinar hosted by our CAMMSE. We probably have more webinar, scheduled down the road. So just watch emails and we will be announcing the webinar, down the road. Okay. Thank you very much again for your time, and I hope you stay safe and healthy during this unprecedented time. Okay. Thank you all.
Thank you, everybody. Thank you, Professor Fan. Yeah, I'll adjourn and jump to the other meeting.
Okay. Thank you, Xianming. Yeah.